Good morning, everyone. Welcome back to the second session of the day. This session is titled More SCA, and we have three different and exciting talks on this. So we'll be exploring different aspects of side channel attack and looking into applications like reverse engineering and how to hack the voice control command of iPhone and Tesla, and finally also how to apply this attack on quantum circuits. So let's get started. So we start with the first talk. The title of the talk is PIRE SCA, Reverse Engineering Black Box Elliptic Curve Cryptography via Side Channel Analysis, and the talk will be given by Jan Janker. Just to mention, this is also the talk with the winner of the Artifact Award yesterday.
All right. Yeah, you can all hear me. Nice. So thanks for coming. My name is Jan Jančar, and I'm a PhD student at the Center for Research on Cryptography and Security at Masaryk University in Brno in Czech Republic. And today I'll be talking to you about, as I pronounce it, PIECka, Reverse Engineering Black Box Elliptic Curve Cryptography via Side Channel Analysis. So this is roughly the outline. I'll first go through why. Why would you want to do that? Why would you want to reverse engineer specifically ECC? And why would you want to use side channel attacks for how they come into play? Then we'll go through these three research questions that we had, focusing on these real-world ECC implementations, then sort of exploring the space of possible ECC implementations, and finally the reverse engineering. So let's start. Elliptic curve cryptography, right? We need some background to understand each other. So we can imagine this is an elliptic curve. This is also an elliptic curve. This is also a different elliptic curve. And finally, this is also an elliptic curve. All these different curve models, equations, whatever. You take one of these, you look at its points over some finite field. They form an abelian group. You have this nice group. You can add these points together. Now, when you can add points together, you can do scalar multiplication, and as we all know, based on this, you can have the elliptic curve discrete logarithm problem, and that's hard given some constraints on the curves and the fields. And on this problem, you can build fancy cryptography, or let's say basic cryptography, like Diffie-Hellman, which is really just a scalar multiplication plus some hash, and out comes the shared secret. Or you can do like ECDSA, which is more involved, right? Random sample, scalar multiplication, some hash, some modular arithmetic, and then you have the signature. Or you can do this Montgomery twisted adversary stuff like XDH or EDDSA or zero-knowledge proofs, pairing-based cryptography, yada yada. There's lots of stuff on elliptic curves. But what's interesting for me, at least, about elliptic curve cryptography is the many implementation possibilities. So right, you can choose the curve model. Right? So let's say you're implementing some curve that's representable in more than one curve model. You can choose which one you're going to be using inside your implementation. Of course, the coordinates. So you have the affine ones, but they are slow. You have projective. You have many other options, extended, and so on and so forth. The addition formulas, right? There's this nice explicit formula database by Dan Bernstein and Tanja Lange, where you can find hundreds of addition formulas for lots of these coordinate systems. They are somehow equivalent, but they are different. You need to pick some. The scalar multiplier, right? You probably need a fixed base multiplier, variable base multiplier, maybe a multiscalar one for ECDSA. You have lots of variants, simple sort of double and add. You can do windows, you can do combs. There's just a ton of stuff there. And finally, the finite field operations. So the lowest level stuff, right? How you do multiplication, how you do squaring, how you do reduction, and inversion. I think the inversion part is kind of popular these days lately with the UC leak attack on the GCD inversion. So what ties this all together is like when you're implementing ECC, whether you pick any of these choices, you need to protect against side channel attacks. So this is just a very quick sort of slide with all the sorts of side channel attacks. There's even more that apply to ECC. We're going to be looking at these three later on. But what they all have in common is assumptions. So what do I mean by assumptions? Well, in most of these papers, you find sentences like something is assumed to be known to the attacker about the implementation. For example, this one assumes like a white box evaluator that knows everything about what's going on inside. This one assumes some sort of binary exponentiation, right? Some double and add. This one assumes that something is done using a downward routine, right? Left to right, not right to left. This one assumes some concrete formulas. This one is a very specific ladder algorithm. This one even full knowledge of all algorithms. So this one assumes just the scalar multiplier and the formulas. So when I say that this is a lot of assumptions you've got there. In all of these papers, right, somehow they contain the sentence that they apply if you know this stuff. But what does reality look like? What do real-world attackers sort of encounter outside, let's say, a certification scenario? Well, I would say that reality looks more like this, right? You have a black box, you have a smart card, you have an HSM, a TPM, whatever. You have it in your card, so you have it in your hands, but it's a black box. But to be more fair to you as an attacker, you can query this black box, right? So you can talk to it, you can communicate, you can perhaps get an oscilloscope, you can measure side channels, EM power, errors, whatever. Now, so why is that? Why are these things a black box? Well, in this cryptographic hardware space, in contrast to the crypto theory space, security by obscurity is still very much alive, right? Like it's being used all the time. Even certifications sort of encourage information hiding, right? So if you're going for CC, you don't want your implementation details to be public, and if attacks require these implementation details, then you get more points, right? The attacks are harder, and so on and so forth. And this is a big contrast to poor August Kerckhoffs, right? Because his principle is being violated here. This is very much not what would happen in the theory space with open design and open discussion. So what all of this creates is a gap. On one side, you have these attacks, right, that assume strong sort of white boxy stuff. They assume knowledge of the implementation. While on the other side, you have targets that are black box. There are lots of choices for the implementation. There's a large space there. So there's a gap in the middle. And what we'll study here, or what this whole paper is about that gap. It's about figuring out, okay, how big of a gap is it? Can we cross it? Can we cross it in an automated way? And is it even a gap? Is there a problem? So we had these 3 research questions to study this gap. The first one is, what implementation choices are used in real-world open source libraries? The second one to sort of study it more combinatorially, how large is the space of all possible ECC implementations? And the third one, whether it's possible to actually automatically reverse engineer these black box ECC implementations. So let's start with the first one. So what we did, we analyzed 18 open source ECC libraries. You can see them there. You can probably also find your own, find your popular library there. And we did source code analysis of these 4 primitives. So this is really the only focus of our paper, nothing more fancy. And we looked at which curve model they used, which scalar multiplier they used, the coordinate system they used, and the addition formulas. You can find the full report on this link. It was a lot of work. This is probably like weeks of going through this code. It's very complicated code. It gets messy. So what we found is that these implementations, these libraries often contain specific implementations, and by that I mean they specify like per curve or per architecture-based implementations, like for this A = -3 or like special fast prime arithmetic. For curve models, usually the outside curve model or like the curve model of the crypto system is usually also used inside. However, for the Montgomery case where you have this twisted Edwards equivalence, sometimes you can do this twisted Edwards thing on the inside. For scalar multipliers, most libraries had these 3 variants of a scalar multiplier for sort of each curve or each implementation. And this was really a jungle. So like the scalar multipliers varied from COMS, fixed windows, this non-adjacent form, GLV. It was even hard to name them, right? Because like you can, a multiplier can just be sort of a combination of several found in the literature. You can take ideas and so on. It's really hard to put proper names to them. And also their parametrizations varied, so like from 4 to 7 bits for the windows and so on. For coordinate systems, it was a bit easier. It's usually Jacobians or like projective Jacobian, but also homogeneous or the XZ for Montgomery stuff. And finally, for addition formulas, which was somehow the trickiest part, we found 112 formula implementations. 50 of them were sort of standard, coming from this EFD database. 23 were out of scope. They were sort of too complicated for our analysis due to reasons. But 39 remaining ones were sort of non-standard. And what I mean by that is that the library likely took some formulas from some paper or from the EFD, and then did some modifications, right? Transformations of the sort like, you have like A plus A and you replace it with like 2 times A. things like that, or maybe even more sort of reordering stuff and so on. And to handle this somehow, or to study this space of transformed formulas, we figured out some transformation and then expanded the set of standard formulas from 200 to roughly 20,000. Now, what is the takeaway from all of this analysis? Is that there is a wide range of actual, like, in real-world implementation choices and real-world implementations. And we would also expect a similarly wide range in black box implementations, of course, with some different constraints, right? On smart cards, you are not like on a server, so you have different constraints, but the variety will likely also be there. Now for the second research question. How large is the space of all possible ECC implementations? And we decided to look at this combinatorically, because you can. It's you know the constraints. For a given curve model, you have some coordinate systems. For those coordinate systems, you have some addition formulas and so on and so forth. And so what we found out, if you can see this table, oh yeah, I guess you can, is that, for example, for the short Weierstrass curve model, there's a total of like 113,000 configurations. And in general, the full total is roughly 140,000. If you look at it by scalar multiplier, you can see that for these, you have like from hundreds to, again, tens of thousands of configurations. What the takeaway is here is that there is actually like the whole space is really quite large. Even though maybe the open source libraries are using sort of small part of it, the whole space is quite large. And what it means for me is that this is something worth reverse engineering, right? Like, you're not just going to guess which one of these configurations your target is just by luck, right? Like, you need some either manual or automated reverse engineering if you don't know. Now, so what's the idea behind this automated reverse engineering? So the main idea, I think, is quite simple, and also I think it's quite elegant, is that you use side channel attacks and turn them around. So these side channel attacks, as I mentioned at the start, so they assume the knowledge of the implementation and they target the key. So what happens if we just assume knowledge of the key, or maybe perhaps even control of the key, and target the implementation? Right, so before the key space, right, it was the key space, so it was like 2 to the 256, so quite large and unstructured. But now sort of the implementation space becomes the key space that we want to search through. And it's nicer, it's only 140,000 entries, they are quite structured, so they have some dependencies and so on. So we get a win there, right? So concretely, we did this for special point-based attacks, because they are particularly nice with this idea, this RPA, so refined power analysis, zero value point attacks, and exceptional procedure attack, I think that's it. And what these attacks all have in common is that they somehow can recognize when a special point appears in scalar multiplication. And by special point, it's kind of hard to describe here, but quite often the special point sort of involves a zero. And so, as we know, like manipulations with zero and multiplication and so on, they can be quite leaky, right? It's a very special value. Zero multiplied with anything, it's still zero, so it propagates, and you have this tricky situation. So the second main idea of this approach is that we can basically use anything, any oracle, any attack, anything, where the behavior of different implementation differs under these attacks, right? So so that's it. So how this sort of works in more detail is that you simulate the behavior of the implementations under the attack, under the oracle, and you build this nice decision table with the answers, where on the left side, on the column, you can see all the sort of configurations. So in this case, we are reverse engineering the scalar multiplier. On the top of the table, over there, you put all your queries that you were asking the implementation, and inside the table you put the answers. Now you have this thing that's called the decision table. A thing like this theory of this thing comes back from the 80s, and from this decision table you can build an optimal decision tree, right? That's just sort of which column questions do you want to ask to optimally sort of figure out which row you're in, right? So in this case, you can see on the right the decision tree is quite simple. You just ask these questions 3, 4, 5, and you figure it out. Now, in RPA, as I mentioned, so this is one variant of our method. In RPA, the question you're asking and basically answering it through a side channel attack is this rth multiple of the input point computed during scale multiplication of k times p by the target, right? So this RPA tag allows you to build this sort of question answering oracle where for a given k that you pick or that's random, you can pick these R values and ask sort of this side channel attack, is this happening in the target? And as you can see, well, from the table, the behavior of these different scalar multiplier differs under this method, right? So, for example, the left to right multiplier computes 2 times p, computes 3 times p for this given scalar, but it doesn't compute 4 or 5 times p. Whereas the right to left computes 2 times p, but doesn't compute 3 or 5 times p, right? This is very simple. You can use this. So we implemented all of this. We have these 3 methods. They have different properties. So by properties, I mean what they target. For example, this RPA method really only targets the multiplier. But it is applicable to any coordinates or any formulas due to the way the attack works. But you need to sort of well, choose or at least have a suitable curve. Not all curves are really suitable for RPA. You need a chosen input point, and you need at least a known scalar. For ZVP or EPA, these other methods, these actually target the coordinates and the formulas, because the behavior of these sort of depends on the coordinates and formulas that are used. But you need to know the scalar multiplier, you need to know the scalar, and again, you need to choose the input point. Now, so we implemented it in this Piecka toolkit, and it works. These are some statistics of these methods. So this column with the C is essentially the number of configurations that these methods are reverse engineering from. This means, like, the first line means you have 34 multipliers. You're trying to figure out which one the target is. For example, the most interesting column, I think, is the expected one with the arrow leaf, which means essentially, on average, how many excuse me, how many queries you need to make to get your answer, right? So that's the sort of the depth of the average depth of the tree. So the answer to this research question is that yes, it's possible. You can automatically reverse engineer black box ECC implementations. And you can do much more. So we have this Piecka toolkit. It stands for Python Elliptic Curve Side Channel Analysis Toolkit. I have stickers if you want. I have hundreds of them, so please come up to me and take them off my hands. And what this toolkit can do for you is much more. It can, enumerate these configurations as I've shown. It can simulate computation given any configuration. That's really nice, I think, for side channel attacks. Like in DPA, you want the intermediate values. You just pick the configuration. You just run some Python, and out they come. You can even generate C implementations of ECC for microprocessors. So we have some sort of code generation based on templates and some fancy scripts, and they essentially generate for any configuration a C implementation that you just then compile, flash, and you can do power tracing, and you can see how it behaves. You can do like power EM tracing. We have picoscope support, chip whisperer support, and so on. There's some processing for the collected traces, alignment, all the good things that you would expect from a toolkit. Really quite nice visualization, quite fast, and it can also perform these known attacks like DPA. It's really there, and finally it can be used to reverse engineer ECC. Right. So to conclude, we documented this large variety of implementation choices in these open source ECC libraries, which was quite a hefty task. I would recommend at least opening at least one, definitely not 18, but like just read through one open source ECC library to see what's out there, if you haven't done that before. And we expect similar variety in black box devices. Of course, this is just an assumption. It may look very different. We would never know without signing some sort of NDAs, right? But we expect to see it. We also explore the space of possible implementation choices of ECC combinatorically, and it's quite large, right? I think you will not be able to guess these. And we presented several sort of novel attack-based reverse engineering methods for ECC and demonstrated in the paper on 2 simulation levels that they actually kind of work. So for more, you can explore our tutorial, which we gave on Wednesday. And you can also like scan this QR code or go to piecka.org and find everything there. So these slides are also contain lots of other interesting references. So I mean, I tried to compile these things that are related to us. For example, these nice 2 examples of manual reverse engineering by people from Ninja Lab and so on. So go check them out as well. So that's it for me. Thanks, and I'm open to questions.
So we have time for some questions. Please approach the mic. Let me check on Zoom. All right. Chan, thanks for the talk. A couple of questions from me. When we were talking about RQ1, right, the research question 1, so do you see any differences in like when you reverse engineer, like any implementation choice which, let's say, make your program a bit harder, difficult to analyze, or like do you see a more uniform pattern over there, like, like in other words, like as a designer, are there ways to make my design more reverse engineer resistant?
Yeah, so one thing I didn't mention at all is countermeasures, right? Of course, if you have side-channel countermeasures and our reverse engineering techniques are using side-channel attacks, then countermeasures against those attacks will stop the reverse engineering from working, right? But like these 3 attacks that we had there, I'm not sure where they are, like RPAs at VP and EPA, these are quite nice because they are resistant to like coordinate randomization, curve randomization, right? So they don't care about these projective sort of randomizations. So that's nice about them. But if you do scalar blinding, then it doesn't work, for example. But you may have different reverse engineering techniques that will work with scale blinding. You just have to do it differently. But like from the open source ECC perspective, that what we were looking at, what was really frustrating, perhaps just frustrating, not really even a blocker for reverse engineering, I think, is that some implementations were really mixing multiple coordinate systems. So you had, like some of these twisted Edwards implementations, you had actually like 3 or 4 coordinate systems that were sort of passing from one to the other, and that's really hard to describe and maybe like enumerate and like play with, right? It's very, very specific.
Exactly. That's what I was also wondering, because you mentioned that there were like non-usual choices as well as many weird implementation of the.
Yeah. So these were usually the choices, right? So I think this LIPS SACP 256K1, this Bitcoin implementation, they have some custom formulas and custom coordinate systems that they pass through. So that's kind of weird. And then the twisted Edwards in Montgomery. Oh, no, actually, just the twisted Edwards implementations tend to be weird.
Any other questions? All right.
Thank you. Sorry, I didn't understand how you validated that your work is working well on. Was it on simulation traces or?
Yeah, so this sort of validation that you see is really just, you take some configurations, you then simulate how the method would work on those configurations. By simulate, I mean like you have full control over, like you're just looking at the intermediate values, you're simulating the oracle, the RPA oracle, is there a 0, is there not? And then you essentially get these trees and you look at the tree metrics and see how well your method would work in practice. But there was another simulation level in which we actually simulated, got actually simulated leakage traces, which basically means that you simulate stuff, you get some intermediate values, you apply a leakage model, you apply some noise, and then you simulate the RPA attack on those traces, and then you use that as an oracle, and we use that to sort of see how these methods would handle noise. More of that's in the paper. But yeah, two simulation levels essentially.
Okay, and did you try it on any hardware?
Good question. Yes and no. So as I mentioned here, the toolkit can generate C implementations. So we tried it on those. However, the toolkit is also using this non-constant time big math library implementation on the inside. And so we sort of, by accident, introduced this misalignment countermeasure in those, right? Because if you have non-constant time math, then it's just very messy. So there it didn't work. But we are working on having a constant time big math implementation in there, and then you can easily test it.
Thank you.
Thanks.
Thanks, Jan, for the great talk. I was wondering, are there other cryptographic primitives where you expect such an incredible heterogeneity in their implementation? Like first part today, and then in 5 years, will there be a need for PyML SCA?
Yeah, I don't know. So I haven't seen it yet. Like, yeah, I mean, in like RSA, you don't have that much. You have the sort of equivalent of the scalar multiplier, right? Because you have the modular exponentiation and you have the finite field stuff, but not this other nice algebraic stuff on top, like coordinates and so on. And in post-quantum crypto, I mean, it's very young, so like I don't know where the implementation is going to go. Like it's hard to predict, right? Maybe, I don't know. Yeah, like if this, like I think if isogeny crypto catches on, like isogeny post-quantum stuff, then that will inherit this ECC diversity. But other stuff, hard to say.
All right, thanks.
Time for one short question. Yeah.
I was wondering, does that work with library with like active kind of measure against side channel attacks, like point randomization and other?
Right. So these methods inherit the resistance of the attacks they're based on. So RPA and ZVP, they're fine with coordinate randomization, right? Because they use these zeros, and these zeros don't disappear if you just like randomize. But they're not fine with like scalar blinding and these sorts of other things, right? But I think the one point that I want to say here is that these countermeasures, and all of them actually, they were designed to protect the key. So, and we don't care about the key. We can control it. We care just about the implementation. So I think there is space for future work that will go around like many countermeasures.
Thank you.
Let's thank Jan again. So we move to the second talk of the session, that is laser-based command injection attack on voice control microphone arrays. And the talk will be given by Hityanshi.
Thanks to the chairs, and good morning, ladies and gentlemen. And my name is Hityanshi, the first author of this essay, and I'm a PhD candidate from Tsinghua University. And today, I'm just going to share with you our works on laser-based command injection attack on voice-controlled microphone arrays. Let's go. So first of all, what is voice control devices? As shown in the picture, you see that there's devices that are equipped with the microphones or on the above or at the side. So that can accurately capture the user's voice command and then responses appropriately. This serves as an interface for human-machine interaction, and allow the users to control other smart devices within the ecosystem through the voice commands. So there are several kinds of microphones. So the first one is called, on the left is micro electrical mechanical system, and we just call it MEMS microphone. And the right one is the electric condenser microphone and some other types. So in this paper, we are mainly focused on the MEMS and the ECM. Both types of microphone utilize condenser structure. As you can see, they are in the similar structures that rely on a capacitor formed between a stationary backplane and a movable diaphragm. So some pressure variations cause the diaphragms to move, altering the capacitor's charge and converting the sound waves into the electrical signal, making them to the laser-based audio injection attacks. So next, integrating the microphone arrays. into the voice control devices is a popular industrial practice due to the enhanced sound pressure and voice recognition capacities they offer. So they are available in 3 main configurations. So the first one is the linear ones and the planar ones and the 3-dimension arrays, which offers the best omnidirectional sound capture, but at the highest cost. So this structure is mainly used in advanced products like Apple HomePod or Huawei's SoundJoy. So voice control devices primarily different from in their microphone structure, so which can be categorized into the single microphone wake-up and the multiple ones. So the distinction is crucial to understand their wake-up mechanism to respond to patterns. In both the figures, red circles mean that the microphone that captures the user's voice command. Typically, voice control devices designed for the single microphone wake-up usually incorporate just 1 or 2 microphones, and any of which can successfully trigger the devices, and then our user got the correct response. But to achieve a successful wake-up for the multiple ones, that the voice commands must to be captured by multiple microphones within the arrays simultaneously. So here's the previous works, and it's called Light Commands, and it's introduced the first laser-based audio injection attack, which can convert the audio commands into the light signal to trigger the voice control devices. However, it mainly triggers the single ones, as I mentioned, and overlooks multiple microphone voice control devices with sensor fusions technology as well, and the non-MEMS microphones types, including the electrical condenser microphone. Strategies like enlarging the laser beams are outdated and ineffective for the targeting microphone areas due to the utilization of the amplitude modulations for the signal conversion in the light commands ways. So it was requiring cumbersome equipment such as the audio amplifiers and the power drivers. It is impossible for our attackers to target the different apertures of the microphone in the array with multiple laser, the laser transmitters. So, for the last but not the least, the manual configurations of modulations parameters make the light commands impractical for multiple microphone devices. So what is our work? In our study, we addressed these challenges for attacking the devices with the microphone arrays, which requires simultaneously control the multiple lasers, and this inspired us to use, that is called the pulse width modulation, PWM, for modulating voice signal based on the hypothesis that the variations in the laser intensity can excite the microphone to generate the right response. So what is PWM? So PWM is the central technique for our works and to convert the analog voice signal into the digital ones. So the process involving modulations the width of the digital signal pulse to reflect the amplitude of the analog signals, as showing the figure right. So the duty cycle of the PWM signal defined that the duty cycle equals to the time on divided by the total period times 100%. So it means the duration of the signal remains high within the total cycle time. So how to get the accurate voice signal sampling according to the Nyquist, it is essential to capture the full informations of audio. So it's post-sampling, the voice signal is converted to the PWM signal, and weird variations in the pulse width are to the audio amplitude, so changes. So such conversion technology, particularly in the use of the unipolar of the PWM signal as shown in the figure. So here comes to our design, which contains 3 main steps. The first is the audio recording and the transmission part. Second is the audio to the PWM signal, and the last is to the modulated laser beams. So, and the key part is our laser control board consists of 3 key modules. First, you see is it's a Bluetooth module and the audio sampling module, and then it's the signal output module. So this is our threat models. So we made a few key assumptions. First, that attackers need to have a clear line of sight to the microphone of the voice control devices. You know, as always, we know that the lights transmit at the directly. You know. So we use the drones or the other tools to adjust the angles. So they are also assumed to have knowledge of the target voice characters, such as the microphone layout. So we need to aim and to transmit precisely the laser to the small microphone apertures. So it is very important. So for the attack methodology, the lasers must to aim precisely, just as I said. So to confirm the success of their attacks, attackers can monitor the feedback of the devices, such as when we speak to our smart speakers, and they will turn on the light and then give us the voice response, you know. And finally, that in the systems with the voice print detection, attackers may pass by these security measures by either force the victim's voice and capture a real sample to mark it. So, as I mentioned before, the sensor fusions cannot be solved by we call the light commands one. So how we figure out these challenges? So we integration of the multiple microphones to enhance. So the sensor fusion typically involves the integrations of multiple microphones to enhance the sound localization and recognition capabilities in voice control devices. For instance, the in-car VC systems utilize multiple microphone areas to figure out that the users to locate at where to it's like a legal area, such as at the front, so the users can only get the response from the front and not in the behind of the cars. So to explore these, we can deceive the voice control system by injecting 2 laser beams, as you can see, it's corresponding to the phase difference delta. The equation 1 and the equation 2 calculated the laser incident angle theta and the corresponding phase difference delta respectively. Attackers can create a phase difference delta in the laser signal, and spoofing the voice control systems, you know, and into recognizing the laser as a legal area signals. So here comes to the attack result, and our study evaluated is 29 mainstream voice control devices modules as listed in the table. So all the devices are successfully be attacked, and including 22 equipped with the microphone array. Notably, that 4 of these in the red box you see could be attacked using the method described in above. What I mean is the light command ones. So while the remaining 18 devices needs to active multiple microphones at the same time for a successful attack. So this table outlines the details of our laser attacks, including the types of the microphones used in each devices and the numbers of the laser required. So we find that the numbers and the position of the microphones being targeting also affect the effectiveness of our attack. The attackers need to inject the laser command into at least 4 adjacent microphones simultaneously to get the devices to respond to their command. So distribute ones is on the left and the adjacent ones on the right, you see. Now, here comes to the most interesting part that I think, that simultaneously aiming the multiple lasers at a decent voice control devices is highly challenging. You know that to address this, we propose to use drones or some vehicles, you know, and other devices to shorten the distance between the attackers and the devices that can ensure the task of the targeting multiple microphone can be accomplished at a relatively shortened area. I also bring our laser transmitters here, and I'm eager to give you a show at here, but you know it's an academic conference, so only the attack demos are available on the website. So if you want, you can see it after. So the flexibility analysis of our works, this analysis encompasses 3 key environmental features: that the thickness of the transparent media, and the colors of the light filters, and the L-shaped structure of the sound path. So our findings detailed in the tables, revealing a remarkable ability of our works to penetrate the board at up to 23.5 millimeters. Yes. And in this experiment, the thickness of the medium is only 2.5 millimeters, and we utilize a laser feature at the 450 nanometers wavelength and average power output of the 400 milliwatts, and we located it and we put it 2 meters distance. We find that the success of related to the B component in the RGB makeups of the filters. So that means the lower B values correlated with the higher penetration rate as shown in the tables. So in this test experiment, we find that even we use the L-shaped structures, it is not work that well. You know that I think we have also said that the active signals consist of 2 parts, and it's the light energy and the signal that's demodulated in the path of the sun. So while the laser injection attack is typically inaudible, the visibility can compromise convert the options. So to address this, we experiment with infrared laser beams. So here's come to some mitigations, and we combine we propose that we should use an L-shaped structure and also the light absorbing materials and optical filters as well. So here's come to some responsible disclosures, and we have informed the affected vendors by Shivam, and the Tianfu is a famous, you know, the security competitions in China. So, and we also work closely to Huawei to strengthen the security of their voice control products. So here's we write down the equation of the photoacoustic effect. Our study extend the advanced work like light commands by demonstrating the various materials, not just the microphone diaphragms can generate the signals. So the table shows the different materials can also demodulate the light, the light signals. So here comes to our future works. So we aim to address the two main challenges. So first is the depending on high aiming precisions, particularly when used the drones, which requires a stable flight for accuracy targeting. Second is the lack of a standline test suite. So here are several related work converting like the audio command injection in inaudible ones, and last is the laser injections ones. So let's draw a conclusion. So our works presents a new approach to the laser-based audio interaction attack for the voice control systems by using PWM modulations for converting the voice commands into the laser signals. And our multiple channel laser arrays effectively trickles the sensor fusion challenges, improving on the method like the light commands. So since no additional signal controller are needed, and the system are easily to scale the target multiple microphones in the areas. So here comes to the end. Thank you for your attention, and for more information, please scan the QR code and to visit our website. Thank you.
Thanks for this talk. We have time for some questions.
My name.
Oh, weird.
So I found that you have the assumption that you can already mimic the sound of for the voice control. So what is the use case that why not you just replay the sound for the attack, or why you try to use the laser attack?
So to some circumstances, it's like a two field that the voice acquisition is I think it's difficult. So that the user's voice, we need to previously record the user's voice in advance. So it's difficult. So we figure out to use some sampling, use the technical ways to how to say that, to make it a fake that can successfully to spoofing the VC systems. Yeah.
Yeah. So another question I want to ask is that because currently we can use AI to mimic,
definitely yes.
Yes. To mimic the voice of someone. So suppose that you are saying other things that we can use AI to make a sound record. It's like that you make the voice command. So for your case, is it possible to extend your work that you already know the sound for someone for other scenarios, and use the AI generated sound and use your laser attack to launch the attack?
Yes, actually the attack scenario that we imagine is the attackers stand outside of the house, and that the voice cannot get through the window. So we use lasers to targeting the smart IoT devices inside of the victim's house. So the lasers can get through it, and then which means that we can control the inside devices, and then basis on this, and we can control the other other devices in the same ecosystems.
Okay, thank you.
Thank you.
I have two small questions. So what will be the cost of this device?
Cost is pretty cheap, as about 348 Chinese yuan per devices.
And do you see like an impact of aging? For example, let's say, as you said, like you're attacking iPhone 15. So if you attack a brand new or something which is 2 years old, like do you see a difference between them or like?
Probably, I think that maybe maybe the vendor's interest is on to capture the high quality voice rather than give the defense on the laser attacks, you know. So although we have tested iPhone 6, 8, even iPhone 15, so probably the same, I think. There's no some mitigations in it.
Yeah, thank you for the amazing talk. I was wondering, are you aware of recent work also on spoofing communication through Windows with lasers? And will the samples collected from there will be enough to have a good model and to reproduce your attack? And if so, will it be possible also with the stability of the drone?
Yes, I have used like in the picture. Oh, come back over. I successfully mount our mount our devices on the drone and to fly outside of the building and to start our attack already. So you see.
Yeah, for the attack it worked, but for the collection of the data voice, for example, you can spoof a discussion inside a building with a laser, observing the frequency of the windows which is vibrating, but I never saw something like that with a drone. So do you think it's possible, or?
Actually, I think it is possible. You know that we can use some cameras, to see the response, and actually the vibrations of, just as you said, the vibrations of the windows. So the laser's energy cannot causes the window to got the vibrations actually.
Yeah, sure.
Yeah.
Okay. And just a side question. So will you recommend to change the color of your windows because some of the colors blocked your attack?
Sorry, again, please.
Okay, no, it was just because with certain colors, your attack didn't work. So maybe we need to change the color of our windows inside the buildings.
Let's thank the speaker again. So we come to the last talk of the session, which is quantum circuit reconstruction from power side channel attacks on quantum computer controllers. The speaker is Farhad Irata, and from what I understand, the talk should be online.
My name is Farhad. I'm going to talk about reverse engineering of quantum circuits from power side channel attacks. It's a joint work between me, my colleague Tranchi Su, and my advisors Rusika Piskac and Jakub Sefer. Let's dive in. The interest in quantum computing has grown rapidly in recent years, and its trend is similar to early stages of Moore's law. And with it grows the importance of securing quantum circuits, especially as these powerful devices begin to be deployed on cloud platforms like IBM Quantum, Microsoft Azure, and Amazon Braket. The intellectual property embedded in quantum programs can be highly sensitive when they are deployed to these cloud machines. While quantum computers offer unique capabilities such as the inability to clone quantum states, making direct information theft more challenging, but they are still vulnerable. The control equipment used to operate quantum systems present potential points of attack, and this area hasn't been thoroughly explored from a security standpoint. Additionally, the physical size of quantum systems makes them more susceptible to physical probing. This figure shows the operation of today's cloud-based quantum computers. Remote users submit jobs to the cloud provider, where the job management or similar server dispatches the jobs to particular quantum computers, also called backends on IBM Quantum. Typically, the digital instructions are sent to controller logic by such as microwave electronics, which generate the actual analog control signals sent to the quantum computer. Our trade model assumes that an attacker can access and collect side channel information from the quantum controller. This is crucial because through side channels like power consumption, we show in this work an attacker can recover control pulses and from there reverse engineer the user's quantum program. This model highlights how an attacker can reconstruct the entire quantum circuit, gaining insight into the computations being run on the quantum device, right? The core of these side channel attacks revolves around the recovery of control pulses, which is typically generated by arbitrary waveform generators, AWGs. An attacker can potentially recover the quantum circuit being executed, and I am going to tell how this can be performed by solving a combinatorial optimization problem. Let's first look at how quantum compilation happens. Similar to classical computing, quantum circuits typically consist of complex instructions. The preparation, compilation, and assembly processes used for classical computing programs are analogous to the activities needed to convert quantum circuits into low-level and hardware-specific instructions before they can actually be executed on quantum computers. Input circuit in the figure, a Qiskit quantum program, this can be as well an open QASM program, is translated into a gate level circuit. The gate level circuit is then transpiled in that involves breaking down non-native quantum gates into groups of native gates, mapping the logic qubits in the original circuits to the physical qubits on the specified quantum computers. Then the transpiled circuit is mapped to a pulse level circuit, which contains information in microwave pulses to regulate and control qubits in the quantum machine. This is also called scheduling. The top figure shows one example quantum circuit. It's a quantum adder, 4 qubits quantum adder, and the bottom figure shows one output circuit after transpilation. All the gates are transformed into native gates on this specific machine, and some operations are added to satisfy the topology of the quantum device. The gates on this figure are RZ, X, SX, and CNOT gates, as you can see. Now, let's look into attackers' measurement capabilities. Each quantum program, that's also quantum circuit, is executed multiple times, and each execution is called a shot. We assume the attacker can sample power traces from shots of a circuit, or they can measure a number of shots, and it is easier to divide this into individual shots, since all shots perform the same operation. Here, single shots, in our case, in our attackers' measurement capabilities, single shot per channel power side channel measurement on the left assumes a stronger attacker model, in which the attacker is able to collect per channel power traces, whereas a weaker attacker could collect a single total power trace over all channels, which can be seen on the right, but not distinguish the power traces of each channel. And the rest of my talk will focus on total power trace attacks. You can find the tables for per channel attacker in the paper. And additionally, our previous CCS work has researched the per channel power traces as well as the timing attacks. However, we did not solve the total power trace attacks. in this work, I'm going to provide you all details how we can use the total power traces to reconstruct the victim circuit, which requires algebraic reconstruction, which requires solving an optimization, combinatorial optimization problem. Figure shows example control passes for the SX, X, and CX gates. You can see the frequency and phase together characterize a pass. The duration, which indicates how long the pass is, amplitude, which indicates how strong the pass is, and other parameters which determine the pass's structure, such as which channels they are sent. All native gates on IBM Quantum have predetermined passes. Here you can see an example victim circuit that is transpiled on 5-qubit IBM Lima machine. The goal is to recover the circuit from its power traces by finding the set of most suitable pass level instructions that make up the circuit with minimum error. Okay, the starting time step here on the table, you can see the start of each pass level instruction are given. If the attacker obtains this information, they can reconstruct the circuit, as the order of the instructions is enough to compile the same circuit again. The third column shows a complete quantum program written in Python that is actually used to generate the circuit on the left. While the per channel attacker aims to recover this table from the measured waveform from each drive channel, the total power trace attacker employs only a single mixed superimposed summed up amplitude samples due to the fact that the attacker does not have access to the individual drive channels. As seen from this figure, the first waveform on the left, on the drive channel on the up, D1 of CX is in the bottom, exactly the same pulse as in SX on the top. So when the pulses are summed up, such as on the right, it is not easy to distinguish them. First, we approach this problem by formalizing the circuit reconstruction problem. For specific quantum machines, we have priors about their pulse characteristic that map to native gates, as I mentioned. For each machine, however, these native gates and their pulse library can differ. Starting from a quantum device D, we specify the set of basis gates, model the set of drive and control channels, capture their channel information as labels, characterize a basis pulse on a channel C. A basis pulse may include pulses on several channels, such as CX gates. They all constitute a basis pulse library. Using the previous set of sets and function definitions, we can specify a pulse level circuit, represents a per channel power trace, also represents a total power trace, which is directly the summation of per channel power traces. We can encode the channel constraints, which means there can only be at most one pulse on each channel at a given time step. This is going to be important when we encode the problem from a given trace. The goal of per channel attacker is to find the circuit from the set of all circuits that minimizes the distance between the total power trace of this circuit and the measured per channel power trace. Similarly, for total power attacker, we want to minimize the power trace of this circuit and the measured total power trace. We can model this problem in linear mixed integer real arithmetic, which is a first order theory that we can solve its instances using an off-the-shelf satisfiable modular theory solver such as Z3. Lyra is a powerful formalism that combines linear equalities and inequalities with arbitrary Boolean connectors and allows us to mix integer and real variables. This makes it highly convenient for modeling our complex reconstruction problem. However, current SMT solvers lack support for optimization problems. It's also worth noting that while SMT solvers can solve the decision variant of the MLP problem, their performance is not as competitive as dedicated MLP solvers. In fact, we couldn't find solutions for simple circuits using SMT solvers. On the other hand, we can effectively solve the problem using MILP solvers. However, MILP only accepts conjunction of linear constraints, and the problem specification need to be convex. Therefore, we need to convert the linear mixed integer linear arithmetic constraints into MILP normal form without exploding the problem in our setting. In order to encode those constraints into MILP normal form, and thereby to perform the side channel attack, we employed various linearization techniques from the operation research community. These techniques involve introducing additional binary variables and bounding them with so-called big M values to convexify non-convex problems that exhibit suitable patterns that I'm going to talk about momentarily. First, we picked a linearizable distance measure for our minimization objectives, which is sum of absolute differences, as our distance function. However, ABS function is not linear, thereby we cannot encode the objective function for an MILP solver. But we use a technique to encode ABS-based objective function in such a way that an equivalent feasible solution can be described by splitting the constraints into two, relaxing the original function into a collection of linear constraints. The logical conditions on binary variables can be also linearized. For instance, not as a function, not of a variable, x can be encoded as 1 minus x, or x1 or x2 can be encoded as their summation, which should be greater than or equal to 1, so on. We can also encode pseudo-Boolean constraints over binary decision variables, such as at most, at least, and exactly constraints by summing up the binary variables having a weight at most 1. In order to encode the channel constraints, we need to linearize the disjunctive constraints. There are two common methods for disjunctions, the big M formulation and the convex hull formulation. In our work, we used a big M formulation where a sufficiently large number M is used to nullify one set of constraints. This is accomplished by adding or subtracting the term M times 1 minus Y to the upper bound and the lower bound constraints respectively. The bounds are chosen such that they are as tight as possible. But we are able to statically over approximate M values in our problem setting, since the decision variable x's are binary variables that can take maximum 1, right? Here I will try to explain an important part of the MILP encoding over an example victim trace. The duration of the trace is 5 dt from dt0 to dt5. The victim runs their circuit on a hypothetical 2-qubit quantum device, D, having only two basis gates, X and SX. We simplify also the notion of label here, since X and SX gates have only one label and waveform. X gate on C1, SX gate on C1, and X gate on C2 are named as X1, SX1, and X2 respectively. The associated pulse waveform for gate SX1 is Gaussian, as you can see on the figure, having 4 sample points. There is another one having 3 sample points, and yet another having only 2 points. Binary decision variables encircled by blue rounded rectangles in the figure indicates all cases where a candidate gate is applied on the channel. For example, at time step dt0, a candidate gate x1 is applied on channel 1, and its pulse contributes to dt1 and dt2 since its pulse waveform has a duration of 3. The other possible cases where the gate can start at are dt1, dt2, and dt3. You can see some other constraints on the sketch, including pseudo-Boolean constraints. For example, there can only be at most one pulse on each channel at a given time step. The objective function is encoded in such a way that it minimizes the error between the victim's power sample, which are black dots at the bottom in the figure you can see, and the goal is to minimize the obsolete error, right? SAD, as I explained before. In our evaluation, we use 3 different IBM quantum computer, T-shape, L-shape, and H-shape. For quantum circuits tested, we use well-known benchmarks from Cousin benchmark suite. The results of our evaluation on benchmark quantum circuits provide compelling evidence of the high accuracy and effectiveness of our techniques in reconstructing quantum circuits. The table shows that we are able to recover all the X, SX, and CX gates from all the benchmarks tested. It's important to note that while our techniques demonstrate high accuracy in reconstructing circuits from power traces, the resulting circuits may not be exact replica of the original circuit, but rather a semantically equal one due to the transpilation procedure I explained in the beginning. This is analogous to the classical compiler optimization where reverse engineering from binary code to the original C code may not yield an exact reconstruction. Thank you. For future research and developments, we aim to investigate defense techniques in order to enhance the security of quantum programs in quantum computing environments. Thank you.